There's a place in our solar system where shadows play tricks on the laws of physics, where darkness doesn't mean absence, but mystery. Pluto, that tiny, distant world at the edge of our cosmic neighborhood, has always been a rebel. Stripped of its planetary title, it refuses to fade into obscurity. Instead, it whispers secrets through the void, sending pulses of invisible light from its permanently shadowed side. Think about that for a moment. A world so far from the sun, where temperatures plunge to unimaginable lows, shouldn't have any light at all, let alone bursts of it flickering like a cosmic Morse code. Yet here we are, staring at data that defies expectation, asking, what is Pluto trying to tell us? This isn't just a puzzle for astronomers. It's a doorway into understanding how the universe operates in ways we've barely begun to grasp. The dark side of Pluto, the hemisphere locked in perpetual night, should be inert, a frozen wasteland untouched by sunlight. But New Horizons, the spacecraft that gave us our first close-up glimpse of this icy outpost, revealed something astonishing. Instruments detected faint, rhythmic pulses of infrared light, a wavelength invisible to human eyes but screaming with significance. What could possibly generate such energy in a place where even the atmosphere freezes and falls like snow? The answer might rewrite textbooks, challenging everything we thought we knew about distant worlds and their hidden dynamism. So let's embark on a journey to the edge of the known, where science meets speculation and curiosity fuels discovery. We'll dive into the leading theories, from subterranean oceans stirring beneath Pluto's crust to exotic chemical reactions on its surface, each one a piece of the puzzle. Along the way, we'll meet the scientists racing to decode these signals, their tools and imaginations pushed to the limit, because this isn't just about Pluto. It's about the hidden rhythms of the cosmos, the subtle ways celestial bodies communicate, and our relentless drive to listen. By the end of this exploration, you'll see that even in the darkest corners of space, light finds a way, and so do we. Pluto's dark side isn't just a frigid, sunless expanse, it's a stage for cosmic contradictions. Imagine standing on that frozen surface, where the sun is nothing more than a distant star, too weak to cast shadows or warm the ground. Yet beneath your feet, something stirs. Instruments aboard New Horizons picked up flickers of infrared light, like a heartbeat in the void, pulsing in rhythms we don't yet understand. This isn't random noise, it's a pattern, a signal from the shadows, and that's what makes it so baffling. On a world where temperatures hover near absolute zero, where even nitrogen and methane freeze solid, how does energy manifest in such precise, intermittent bursts? One leading theory points to Pluto's underground ocean, a sloshing, briny layer trapped beneath miles of ice. If it exists, tidal forces from its moon Charon could be squeezing this hidden sea, generating heat and pressure that crack the surface above. Geysers of volatile gases might erupt, freezing instantly in the vacuum of space and scattering particles that catch the faintest glimmers of sunlight. But here's the twist: these pulses don't always align with Charon's gravitational tugs. Some scientists suggest another culprit: exotic ices like methane or nitrogen clathrates, which trap gases in cage-like structures. When these ices fracture or shift, they could release stored energy in sudden, luminous flashes. Then there's the solar wind, a stream of charged particles racing from the sun. While Pluto's thin atmosphere usually shields its surface during certain orbital phases, the solar wind might breach its defenses, sparking chemical reactions in the ices. Think of it like static electricity on a cosmic scale, tiny discharges lighting up the darkness. But even this explanation falls short. Other Kuiper belt objects, like Eris or Makemake, endure similar conditions without flickering like Pluto does. So why is Pluto special? The answer might lie in its chaotic past. Collisions, orbital shifts, or even the remnants of a warmer core could have left Pluto with a unique geological fingerprint. Every pulse we detect is a clue, a whisper from a world that refuses to be silent. And as telescopes grow sharper and missions more ambitious, we're inching closer to deciphering this cryptic language. What we learn won't just rewrite Pluto's story. It could redefine how we see all icy worlds at the edge of the solar system. Because if darkness can flicker with light here, what other surprises are waiting in the cold, quiet corners of the cosmos? The invisible dance of light on Pluto's dark side isn't just a curiosity, it's a language written in wavelengths our eyes can't see. Infrared and ultraviolet emissions, those hidden signatures, tell a story far richer than we ever imagined. When New Horizons caught those rhythmic pulses, it wasn't just capturing noise, it was eavesdropping on a conversation between Pluto's surface and the cosmos. Infrared light, with its ties to heat, suggests something is stirring beneath the icy silence. Picture this, even in a world where surface temperatures plunge to -390 degrees Fahrenheit, pockets of warmth might persist, hinting at residual geothermal activity or chemical reactions brewing in exotic ices. It's like finding a whisper of steam in a freezer, a paradox that defies intuition. Then there's the ultraviolet flashes, the cosmic fireworks no human eye has witnessed. These bursts point skyward, implicating Pluto's wispy atmosphere. On Earth, we see auroras paint the polar skies when solar wind collides with our magnetic field. But Pluto lacks a strong magnetic shield, so what's sparking these UV glimmers? One possibility: charged particles from the solar wind slipping through cracks in Pluto's atmospheric defenses, exciting molecules like nitrogen and methane until they release energy as ultraviolet light. Another theory suggests cosmic rays, high-energy particles from deep space could be the trigger, slamming into Pluto's surface ices and kicking off cascades of reactions. Either way, these flickers are proof that even a world without a traditional magnetic field can host its own version of celestial light shows. What's truly groundbreaking is how these findings shatter the old image of Pluto as a stagnant, frozen relic. Infrared pulses imply internal heat, maybe from a subsurface ocean slowly churning, its tides flexed by Charon's gravity. Or perhaps radioactive elements in Pluto's core still decay, offering faint warmth like dying embers in a hearth. Meanwhile, ultraviolet flashes suggest an atmosphere more dynamic than we thought, one that doesn't just freeze and collapse but crackles with unseen energy. Together, these clues paint Pluto not as a dead rock but as a world with a hidden heartbeat. This isn't just about rewriting Pluto's resume, it's about redefining what dwarf planets can be. If Pluto, small and distant, harbors such complexity, what does that mean for Eris, Haumea, or the other icy bodies in the Kuiper belt? Suddenly, the outer solar system seems less like a graveyard and more like a stage where frozen worlds pulse with quiet, invisible life. Every flicker of infrared, every flash of ultraviolet is a challenge to our assumptions, pushing us to look deeper, listen closer, and wonder what else we've underestimated in the dark. NASA's New Horizons spacecraft didn't just give us a snapshot of Pluto, it handed us a mystery wrapped in ice. When it zipped past the dwarf planet in 2015, its cameras and sensors were trained on the sunlit hemisphere, capturing heart-stopping details of towering mountains and sprawling glaciers. But the real surprise lurked in the shadows. Even as the mission's primary focus was the illuminated side, its instruments couldn't ignore the faint, ghostly signals coming from the dark half. the side that should have been a frozen, lifeless slab. Instead, New Horizons detected temperature spikes where none should exist, like a fever in the void, and whispers of gas escaping from a surface that was supposed to be locked in perpetual stasis. These weren't random blips in the data. The spacecraft's infrared spectrometer picked up rhythmic fluctuations, as if something beneath the ice was breathing. And then there were the ultraviolet signatures, fleeting but unmistakable, hinting at gases like nitrogen or methane seeping into the tenuous atmosphere before freezing back onto the surface. It's as if Pluto's dark side isn't dead at all, but simmering with slow, cryptic activity. Scientists combing through the data have proposed wild theories. Maybe underground reservoirs of slushy water are belching gases through cracks in the ice, or sunlight scattered by interplanetary dust is somehow reaching the unlit terrain, triggering chemical reactions we don't yet understand. But here's what makes New Horizons' findings so groundbreaking. They weren't designed to study the dark side at all. The mission's instruments were optimized for Pluto's sunlit features, yet the dark side's anomalies were so persistent, they forced their way into the data like uninvited guests. That's the thing about exploration. Sometimes the biggest discoveries aren't in the places you're looking, but in the corners you barely glance at. And now, nearly a decade later, researchers are still mining that trove of information, running new simulations and revisiting old assumptions, because Pluto's dark side refuses to fit neatly into any textbook model. What New Horizons glimpsed was more than just a scientific oddity. It was a challenge to our understanding of how distant, icy worlds behave. If Pluto, a tiny outpost at the solar system's edge, can harbor such unexpected dynamism in its shadows, what does that mean for other frozen realms in the Kuiper belt? Every flicker of heat, every trace of gas, is a thread in a larger cosmic tapestry we've only just begun to unravel. And as New Horizons speeds deeper into the void, its legacy isn't just the stunning images it sent home, it's the questions that keep us staring into the dark, wondering what else we've missed. Pluto's frozen skin is far more than just a barren sheet of ice. It's a volatile, ever-changing mosaic where chemistry defies the cold. Picture a landscape where nitrogen, methane, and carbon monoxide don't just sit idly like frost on a windowpane. Instead, they shift, crack, and sometimes vanish entirely, transforming directly from solid to gas in a process called sublimation. On a world where the sun is a pinprick in the sky, these ices cling to every crater and plain, but their behavior is anything but predictable. When even the faintest sunlight grazes Pluto's dark side during its 248-year-long orbit, these exotic ices don't just passively reflect light, they might actively create it. Here's how: as sunlight, however weak, hits methane or nitrogen ice, photons can kickstart photochemical reactions, breaking apart molecules and leaving behind charged fragments. These fragments, desperate to regain stability, release energy in the form of infrared or ultraviolet light. It's like striking a match in slow motion, a delayed, flickering glow invisible to our eyes but screaming its presence to sensors. And because Pluto's rotation is tidally locked with Charon, its dark side isn't always uniformly dark. During seasonal transitions, slivers of sunlight might creep into shadowed regions, triggering these reactions in brief, rhythmic bursts. But there's another, deeper layer to this puzzle. Some researchers suspect Pluto's core might still harbor traces of radioactive elements like potassium or uranium, remnants from the solar system's violent birth. As these elements decay over billions of years, they release heat, not enough to melt the ice above, but perhaps sufficient to create localized warm spots. Imagine a radiator buried under miles of frozen nitrogen, its warmth occasionally seeping through cracks, causing pockets of ice to sublimate or even triggering chemical chains we've yet to map. The wild card, exotic ices like methane clathrates cage-like structures that trap gas molecules in their crystalline grip. Under the right conditions, these clathrates can fracture, releasing trapped gases in sudden, energetic bursts. It's like opening a shaken soda bottle in slow motion, with the escaping gas carrying enough energy to emit faint pulses of light. If Pluto's surface is riddled with these unstable structures, their collapse could explain the intermittent flashes New Horizons detected. What makes this so thrilling is how it turns conventional wisdom on its head. We used to think of Pluto's surface as a static museum exhibit frozen in time. Now we're seeing it as a lab where chemistry and physics conspire in ways we're only beginning to decode. Every pulse of light, every whiff of escaping gas, is a clue that this dwarf planet is anything but dormant. And if Pluto's ices are this active, what does that mean for the other frozen worlds lurking in the Kuiper belt's shadows? Suddenly, the edge of our solar system feels less like a freezer and more like a simmering kitchen, where ingredients we've barely catalogued are cooking up surprises we've yet to taste. Pluto's atmosphere is so thin you could barely call it an atmosphere at all, more like a wisp of gas clinging desperately to the surface. Yet this fragile envelope holds the key to some of the dwarf planet's most baffling behaviors. Unlike Earth's thick, protective blanket, Pluto's air is a transient thing, swelling and collapsing with the seasons like a celestial lung. When Pluto swings closer to the Sun during its elongated orbit, solar warmth coaxes nitrogen, methane, and carbon monoxide ices into vapor, briefly puffing up the atmosphere. But as it retreats into the cold depths of the Kuiper belt, that same air freezes back onto the surface, falling as snow over glaciers of solid nitrogen. This dramatic cycle doesn't just change Pluto's weather, it might be powering those mysterious pulses of light. Think of it like a planetary pressure cooker. As the atmosphere expands, it creates shockwaves, subtle ripples of compression that travel across the surface. When these waves collide with patches of volatile ices, they could trigger tiny explosions of sublimation, releasing bursts of gas that scatter infrared light like cosmic fireworks. Even more intriguing is the role of the solar wind, that relentless stream of charged particles from the sun. Without a strong magnetic field to deflect it, the solar wind slams directly into Pluto's tenuous atmosphere, ionizing molecules and potentially sparking faint auroras. These wouldn't be the dazzling curtains of light we see on Earth, but something far more ghostly, dim flickers of ultraviolet or infrared glowing where the solar wind excites nitrogen or methane molecules. The real puzzle is timing. Pluto's light pulses aren't constant. They come and go in rhythms that don't always match its seasons or orbital quirks. That inconsistency suggests something else is at play, perhaps pockets of unusually volatile ices, or hidden geysers erupting from beneath the surface, injecting fresh gas into the atmosphere at irregular intervals. It's as if Pluto's thin veil of air is a canvas, and every flicker of light is a brushstroke painted by forces we're only beginning to untangle. What's astonishing is how much chaos can unfold in such a sparse environment. Earth's atmosphere is a roaring symphony compared to Pluto's whisper, yet this delicate system manages to host dynamic processes that rival those of larger planets. Every pulse of light, every wisp of escaping gas is a reminder that even the faintest atmospheres can harbor surprises. And as we study Pluto's quirks, we're not just decoding one world, we're learning how countless other icy bodies, from distant dwarf planets to moons like Triton, might hide their own cryptic light shows in the dark. The solar wind doesn't care about darkness. This relentless stream of charged particles, racing outward from the sun at nearly 1 million miles per hour, reaches even the farthest corners of the solar system, including Pluto's shadowed side. When these high-energy particles slam into Pluto's tenuous atmosphere or its frozen surface, something extraordinary happens. The collision can strip electrons from atoms, a violent handshake between the solar wind and Pluto's sparse gases. This process, called charge exchange, releases energy in the form of ultraviolet or even X-ray light, invisible to our eyes but blazing with information. It's like sparks flying when a hammer strikes metal, only on a cosmic scale where the hammer is the sun's fury and the metal is Pluto's icy crust. But here's the mystery. Charge exchange usually requires a magnetic field to funnel particles, like Earth's auroras dancing along magnetic lines. Pluto, though, has no strong magnetic shield, so how does the solar wind ignite these light shows without one? One theory suggests Pluto's atmosphere, thin as it is, acts like a sieve. Charged particles slip through its gaps, striking surface ices rich in nitrogen and methane. When they hit, the energy released could kick electrons into higher orbits, and as those electrons settle back down, they emit ultraviolet flashes. It's a bit like knocking over a domino. The initial impact sets off a chain reaction of energy release, culminating in a flicker of light. What's even stranger is the timing. Solar-wind interactions should be constant, yet Pluto's light pulses are irregular. This hints at something else at play. Maybe the solar wind isn't acting alone. Pluto's orbit is elliptical, bringing it closer to the Sun at times, then flinging it farther away. During its closer approach, the solar wind intensifies, potentially supercharging these reactions. But when Pluto retreats, the solar wind weakens, and the light shows might fade or change rhythm. There's also the wild card of interplanetary magnetic fields, which can twist and redirect the solar wind in unpredictable ways, like cosmic weather altering the path of a storm. The real clue lies in comparing Pluto to other worlds. Venus, Mars, and even comets exhibit charge exchange, but none pulse quite like Pluto. That uniqueness could be due to its exotic surface chemistry, ices we rarely see elsewhere, cracking and sublimating under the solar wind's assault. Or perhaps it's the way Pluto's atmosphere freezes and thaws over centuries, creating a feedback loop where gas escapes, reacts, and then snows back down, resetting the stage for the next light show. Every flicker of ultraviolet or X-ray light is a breadcrumb leading us closer to understanding how small, icy worlds interact with the solar wind. If Pluto, a tiny dwarf planet with no magnetic field, can produce such dynamic displays, what does that mean for the other frozen relics in the Kuiper belt? The solar wind might be the unseen artist painting the darkness with light, and Pluto is its most surprising canvas. Beneath Pluto's icy crust, there might be an entire ocean hiding in the dark, a secret reservoir of liquid water defying the bitter cold of space. It sounds like science fiction, but the math checks out. Radioactive elements like potassium and uranium, remnants from the solar system's birth, could still be decaying in Pluto's core, generating just enough heat to keep water liquid under miles of ice. Add Charon's gravitational tug, flexing Pluto's interior like a stress ball, and you've got a recipe for a subsurface sea. This isn't just speculation, we've seen it elsewhere. Jupiter's moon Europa and Saturn's Enceladus both hide oceans beneath their frozen shells, with geysers erupting into space. If Pluto joined this club, it would rewrite the rules for how small, distant worlds behave. Now imagine that ocean's surface, not waves under a blue sky, but a black abyss capped by a ceiling of ice. Occasionally, that ice fractures. Heat from below surges through the cracks, vaporizing pockets of nitrogen or methane ice near the surface. The resulting gas bursts into Pluto's thin atmosphere, carrying with it traces of infrared or ultraviolet light. These wouldn't be massive eruptions, but tiny, rhythmic whispers, just enough to explain the flickers New Horizons detected. The timing might seem random, tied to the slow grind of ice shifting overhead or the occasional quake as Charon's gravity squeezes Pluto's core. But here's the catch. Proving this theory is like trying to study a buried lake by listening for ripples through a mile of concrete. The evidence is indirect, a subtle wobble in Pluto's rotation, hints of fresh ice in certain craters, or the way its surface seems oddly young for a world that should have been geologically dead for eons. Each clue is a breadcrumb pointing to something stirring below. What makes this idea so compelling isn't just the science, it's the implications. If Pluto has an ocean, it joins an elite group of worlds where liquid water exists against all odds. And where there's water, there's potential, not for little green men, but for chemistry that could, under the right conditions, nudge the universe toward life. Even if that's a long shot, the mere possibility transforms Pluto from a frozen curiosity into a frontier. Every unexplained pulse of light becomes a question. Is this the moment a crack opened, a geyser sputtered, or an ocean sighed in the dark? Until we send another mission to listen more closely, Pluto's secrets will stay half-told, dangling between data and dream. Charon isn't just Pluto's moon, it's a gravitational heavyweight, locked in a cosmic tug of war with its dwarf planet partner. These two worlds orbit so closely that they're practically hugging, separated by just 12,000 miles, less than the distance between Earth and some of our high-flying satellites. But this intimacy comes with consequences. Charon's gravity doesn't just gently pull on Pluto, it twists and stretches its interior like taffy, generating heat through friction. Picture squeezing a stress ball over and over. Your hands warm up from the effort. Now imagine that on a planetary scale, where Charon's relentless tug churns Pluto's rocky core, creating pockets of warmth that defy the frozen void around them. This tidal heating could be the engine behind Pluto's mysterious light pulses. As Charon's gravity flexes Pluto's crust, it might crack open fissures in the ice, like wrinkles forming on a sheet of glass. Through these fractures, gases trapped beneath nitrogen, methane, even whispers of water vapor could escape, bursting into the thin atmosphere. When sunlight, however faint, hits these plumes, it could trigger chemical reactions that release energy as infrared or ultraviolet flashes. It's a chain reaction with Charon as the instigator, yanking on Pluto's interior until something gives. But here's where it gets stranger. Pluto and Charon are tidally locked, always showing the same face to each other, like dancers spinning endlessly without ever letting go. This means Charon's gravitational pull isn't evenly distributed. It tugs hardest on the side of Pluto closest to it, creating a lopsided strain. Over time, this could warp Pluto's crust, leading to uneven stress points where activity concentrates. Some scientists speculate that these strained regions might become hotspots for geysers or cryovolcanos, spewing icy slurries onto the surface. If so, Charon isn't just a passive moon, it's an architect, reshaping Pluto's geology from the inside out. The real twist: Charon might not be working alone. Smaller moons like Styx, Nix, and Hydra add their own subtle tugs to the mix, creating a gravitational symphony that keeps Pluto's interior in flux. While their influence is weaker over billions of years, even tiny nudges could contribute to the chaos beneath Pluto's ice. Together, these moons might be stirring the pot, ensuring Pluto never fully settles into stillness. What makes this dance so fascinating is how it mirrors other odd couples in the solar system. Jupiter's moon Io, for example, is stretched so violently by its host planet's gravity that it's the most volcanically active world we know. Pluto's situation is quieter but no less profound, a slow-motion version of the same forces playing out in the Kuiper belt's deep freeze. If Charon's tug is indeed cracking Pluto open, it suggests that even small, distant worlds can harbor hidden fire beneath their icy shells. And if that's true, the dark side's flickering light might not be a mystery at all, just the glow of a world being pulled apart and stitched back together, over and over, by the moon it can't escape. Pluto doesn't just orbit the sun, it drifts through time on a scale that dwarfs human experience. A single trip around the sun takes 248 Earth years, meaning most seasons stretch longer than civilizations. Imagine a winter so deep it lasts 6 decades, where the sun shrinks to a faint star and the atmosphere collapses like a deflated balloon, freezing solid onto the surface. Then, as Pluto inches closer to the sun, that same nitrogen snow vaporizes back into a wispy haze, and the landscape stirs with changes too slow for any one observer to witness. These aren't just weather patterns, they're planetary metamorphoses, and they might hold the key to the dark side's eerie light shows. Think of Pluto's seasons like a pendulum swinging in extreme slow motion. During its brief summer, when the sun's feeble warmth reaches the dwarf planet, sunlight could penetrate thin patches of ice, triggering chemical reactions in volatile compounds like methane or carbon monoxide. These reactions might release energy in sporadic bursts, infrared flickers, or ultraviolet flashes like dormant fireflies waking under a heat lamp. But here's the twist, because Pluto's axial tilt is extreme, roughly 120 degrees compared to Earth's 23, its poles take turns facing the sun for stretches lasting nearly a century. That means the dark side isn't always the same hemisphere. A region plunged in shadow for decades might suddenly bask in twilight, its frozen surface cracking under the strain of newfound warmth, venting gases that glow under the solar wind's assault. The lag between cause and effect is where things get fascinating. Pluto's surface ices don't respond instantly to temperature shifts. They're insulators, resisting change like a glacier reluctant to melt. A pulse of heat might take years to seep through layers of nitrogen and methane ice, meaning a burst of light detected today could be the delayed echo of a solar touch from decades ago. It's like pressing your hand into memory foam. The impression lingers long after you've let go. This hysteresis effect could explain why Pluto's dark side doesn't emit light consistently, even during seasonal transitions. The system isn't just slow, it's a cosmic game of telephone where signals get distorted over time and distance. Yet there's another layer to this seasonal puzzle. Pluto's orbit isn't a perfect circle. It's a lopsided ellipse that brings it closer to the Sun than Neptune for 20 of those 248 years. During this perihelion summer, solar radiation intensifies just enough to supercharge surface chemistry. Models suggest this could create feedback loops. More sublimation thickens the atmosphere, which traps more heat, leading to more sublimation. If the dark side's pulses are tied to this cycle, they might crescendo as Pluto nears the Sun, then fade into silence as it retreats. But with our current data, captured during just a sliver of Pluto's year, we're like ants trying to predict the tides after watching the ocean for 5 minutes. What's humbling is realizing how much we're missing. A full Plutonian year hasn't been observed since its discovery in 1930. Even the data from New Horizons, our fastest, farthest-reaching scout, represents less than 1% of a single seasonal cycle. Every strange glow, every wisp of gas, is a snapshot of a process that unfolds over lifetimes. To truly decode these rhythms, we'd need missions that outlast their creators, or telescopes patient enough to watch Pluto's slow dance for centuries. Until then, the dark side's intermittent light remains a message in a bottle, tossed into the cosmic ocean with no return address. a reminder that some mysteries operate on clocks we can't yet read. Imagine a volcano, but instead of fiery lava, it erupts with a frozen slurry of water, ammonia, and methane, oozing across the landscape like glacial toothpaste. This is cryovolcanism, and Pluto might be hiding these icy fireplaces in its darkest corners. While Earth's volcanoes reshape continents with molten rock, Pluto's potential cryovolcanoes would sculpt its surface with slow-motion explosions of slush, leaving behind domes and plains of frozen chemicals. New Horizons spotted two massive mounds, Wright Mons and Pickard Mons, each stretching over 100 miles wide and towering several miles high structures eerily similar to known cryovolcanoes on moons like Triton or Europa. But here's the catch: on Pluto, these features could be dormant, or they might still be alive, exhaling gases that catch the faintest starlight. What makes cryovolcanism so compelling isn't just the spectacle, it's the chemistry. If these icy volcanoes are active, they could be belching nitrogen, methane, or even carbon monoxide into Pluto's thin atmosphere. Sunlight, though weak, would then break apart these molecules, triggering reactions that release energy as infrared or ultraviolet light. Picture a geyser on Earth glistening in the sun, except here, the eruption is a slow-motion fountain of volatile ices, and the glow is invisible to human eyes. Even more intriguing, the solar wind could ionize these gases, sparking ephemeral auroras over the volcano's summit. It's a light show powered not by fire, but by frost. The trouble is proving it. From 4 billion miles away, a cryovolcanic plume would be fainter than a candle on the horizon. New Horizons' fleeting flyby gave us just a snapshot, and without repeated observations, we can't say for sure if those domes are fresh or fossilized. Some researchers argue the structures might be relics of a warmer past, when Pluto's interior heat was enough to drive icy eruptions. Others point to the lack of impact craters on their slopes, a hint they could be young, reshaped by recent activity. Then there's the wild card. Radioactive decay in Pluto's core might still be providing just enough warmth to keep certain volatiles mobile, like a battery on its last legs powering a flickering bulb. If Pluto's cryovolcanoes are active, even sporadically, they'd rewrite the rules for what small, cold worlds can do. Most dwarf planets were assumed to be geologically dead, their interiors frozen solid eons ago. But cryovolcanism suggests they might simmer with hidden energy, their ice shells cracking under pressure like a soda can left in the freezer. Every pulse of light from Pluto's dark side could be the signature of these icy eruptions, a slow, silent fireworks display at the edge of the solar system. Until we send another mission to listen for their heartbeat, the question lingers: is Pluto whispering to us through the glow of its frozen volcanoes? Pluto's dark side shouldn't glow, that's the rule. But rules in the outer solar system are more like suggestions, and Pluto loves breaking them. Here's the twist: even without sunlight, chemical reactions on its frozen surface might be conjuring their own eerie light. Picture this: cosmic rays, high-energy particles racing across the galaxy slam into Pluto's methane and nitrogen ices like microscopic bullets. The impact fractures molecules, leaving behind charged fragments desperate to regain stability. As these shattered pieces recombine, they release energy in the form of faint, ghostly light. It's called radioluminescence, and it turns Pluto's ices into a cosmic glow in the dark sticker, flickering in the void. This isn't just theoretical. On Earth, we've seen similar glows in radioactive minerals like autunite, which emit a soft greenish light as they decay. But Pluto's version is far more exotic. Its ices aren't just passive reflectors, they're active participants, transforming the violence of cosmic rays into silent sparks. The solar wind adds another layer to this alchemy. Charged particles from the Sun, though sparse at Pluto's distance, can penetrate thin patches of ice, exciting molecules until they release ultraviolet or infrared flashes. It's like rubbing a winter mitten against a wool sweater in the dark, except instead of static electricity, you're seeing the aftermath of interstellar particle collisions. What's fascinating is how unpredictable this glow would be. Cosmic rays don't arrive in neat, rhythmic patterns. They're chaotic, peppering Pluto's surface at random. Yet New Horizons detected pulses that seemed almost organized. This mismatch suggests something else is at play. Maybe the ices themselves are structured in a way that amplifies or channels the light. Methane clathrates, with their cage-like molecular prisons, could trap energy until it builds to a breaking point, releasing it in sudden bursts. Or perhaps Pluto's terrain has hotspots, areas where the ice is unusually pure or thick, acting like cosmic neon signs when struck by particles. The implications stretch beyond Pluto. If radioluminescence is real there, it could be happening on other Kuiper belt objects too. Worlds like Makemake or Haumea, where methane and nitrogen coat the surface. Suddenly, the outer solar system isn't just a graveyard of frozen relics. It's a gallery of faint, flickering canvases, each telling a story written in particle impacts and molecular whispers. And here's the kicker: this light isn't for us. Human eyes would never see it. It's a hidden language spoken in wavelengths only machines can decode, reminding us that the universe doesn't need an audience to create wonders. So the next time you hear about Pluto's dark side pulsing with invisible light, remember, it's not a malfunction in the data. It's chemistry and physics dancing in the dark, turning cosmic violence into something almost beautiful. And if that's happening on Pluto, what other luminous secrets are waiting in the shadows of the Kuiper belt? The answer might be written in light we've yet to learn how to see. Cosmic rays are the universe's way of whispering secrets in a language we're only beginning to understand. These high-energy particles, born in the violent hearts of supernova or the jets of distant black holes, race across the galaxy at nearly the speed of light. Pluto, despite its isolation, isn't spared from this relentless bombardment. Every square inch of its frozen surface is a target, struck countless times by particles packing more energy than anything we could produce in Earth's mightiest accelerators. When these cosmic bullets hit Pluto's methane, nitrogen, or carbon monoxide ices, the collision isn't just a quiet tap, it's a microscopic explosion. Molecules shatter, electrons are torn free, and for a fleeting instant, the void around Pluto crackles with invisible energy. What happens next is like a cosmic game of dominoes. The wreckage of those shattered molecules, charged fragments, and free electrons desperately seek stability. As they recombine, they release their excess energy in the form of photons, some glowing in infrared or ultraviolet wavelengths. This phenomenon, called secondary radiation, might explain the flickers New Horizons detected. The timing fits too. Cosmic rays don't arrive in steady waves. They come in unpredictable bursts, like raindrops on a tin roof. That randomness could account for why Pluto's dark side pulses aren't regular. They're echoes of chaos from across the galaxy. But here's the catch: these light shows are incredibly faint. Earth's atmosphere shields us from most cosmic rays, but Pluto has no such luxury. Its surface is a naked frontier, exposed to the full fury of deep space. To detect the faint glow from cosmic ray impacts, you'd need instruments far more sensitive than anything New Horizons carried. Future missions might include detectors specifically tuned to catch these elusive signals, like microphones listening for the faintest footsteps in a silent room. What makes this theory so compelling is its universality. Cosmic rays aren't unique to Pluto. they rain down on every world from Mercury to the moons of Neptune. Yet Pluto's peculiar chemistry might amplify their effects. Its ices aren't just passive bystanders, they're active participants in this high-energy dance. Methane, for example, is particularly good at absorbing cosmic ray energy and re-emitting it as light, a process called scintillation. On Earth, we use synthetic scintillators in particle detectors to catch cosmic rays. Pluto's surface could be doing the same thing naturally, turning the entire dwarf planet into a makeshift cosmic ray observatory. The implications stretch beyond one icy world. If cosmic ray impacts are indeed lighting up Pluto's dark side, the same could be happening on other Kuiper belt objects with similar surface compositions. Eris, Makemake, or Haumea might also flicker in the dark, their surfaces alive with silent sparks from interstellar bullets. Suddenly, the outer solar system isn't just a collection of frozen relics, it's a vast, interconnected network of cosmic ray detectors, each pulsing with stories from the galaxy's most violent events. Yet for all its elegance, this explanation isn't perfect. Cosmic ray impact should produce a steady background of faint light, not the intermittent pulses we've observed. That discrepancy suggests something else is at play. Perhaps cosmic rays are just one piece of a larger puzzle. Maybe they're triggering chain reactions in Pluto's ices, causing pockets of gas to build up and release in sporadic bursts. Or their energy could be destabilizing fragile clathrate structures, leading to delayed light emissions. Whatever the case, these high-energy particles are more than just interstellar noise. They're clues etched in light, waiting to be decoded. So while cosmic rays alone might not solve Pluto's dark side riddle, they open a window into a hidden layer of solar system physics, one where the smallest particles can illuminate the grandest mysteries. Every flicker from Pluto's shadows is a reminder that even in the emptiest reaches of space, nothing is truly quiet. The universe is always speaking, if we're patient enough to listen. Magnetism might be the missing key to Pluto's dark side light show, but here's the catch. We're not even sure if Pluto has a magnetic field at all. Earth's vibrant auroras are born from our planet's robust magnetic shield, funneling solar wind particles toward the poles in dazzling displays. If Pluto had even a whisper of its own magnetic field, no matter how faint, it could sculpt those mysterious light pulses into something resembling celestial fireworks. Picture charged particles spiraling along invisible magnetic lines, crashing into Pluto's thin atmosphere and sparking ultraviolet or infrared glows. It's a compelling idea except for one glaring hole in the theory. New Horizons didn't detect a global magnetic field during its flyby, leaving scientists with more questions than answers. But absence of evidence isn't evidence of absence. Some researchers argue Pluto might harbor patchy, localized magnetic zones, remnants of a once active core. Imagine pockets of magnetism frozen into the crust, like ancient compass needles locked in ice. If solar wind particles hit these zones just right, they could trigger sporadic bursts of light, explaining why the pulses aren't uniform. There's also the wild card of induced magnetism. When the solar wind slams into Pluto's atmosphere, it might generate temporary magnetic ripples, a phantom field flickering in and out of existence. These fleeting forces could redirect particles toward the surface, igniting tiny, transient auroras in the darkness. The real twist, Pluto's moon Charon might be muddying the magnetic waters. Charon shows signs of past geologic activity, and some models suggest it could have its own weak magnetic interactions. As the two worlds orbit each other, their gravitational dance might stir up electromagnetic eddies, creating hybrid phenomena neither body could produce alone. It's like two singers harmonizing a duet of forces that transforms silence into song. Yet for all these possibilities, the truth remains elusive. Without another mission to map Pluto's magnetic environment in detail, we're left with tantalizing maybes. What makes this mystery so gripping isn't just the science, it's the sheer audacity of the idea. A tiny, icy world at the solar system's edge, defying expectations by conjuring light through forces we can't yet measure. If Pluto does have a magnetic whisper, however faint, it would rewrite the rules for how small, cold worlds interact with the cosmos. And if it doesn't, well, that just means the true source of those pulses is even stranger than we imagined. Dark matter is the universe's most elusive ghost, invisible, untouchable, and yet somehow holding galaxies together with its gravitational grip. Could this mysterious substance also be responsible for the flickering light on Pluto's dark side? It sounds like science fiction, but a handful of theorists have dared to ask the question. The logic, however speculative, goes like this. If dark matter particles occasionally collide with each other or with normal matter, they might release energy in the form of light, usually too faint to detect, but perhaps amplified by Pluto's unique environment. Imagine dark matter flowing through the solar system like an intangible river, pooling in the gravitational wells of distant worlds. If Pluto's icy crust acts as a lens, concentrating these particles, their rare interactions could spark the faint pulses we've observed. Of course, mainstream astrophysics raises an eyebrow at this idea. Dark matter's effects are typically seen on galactic scales, not in the backyard of a tiny dwarf planet. The leading models suggest dark matter is cold, slow-moving and aloof, rarely interacting with ordinary matter except through gravity. For it to suddenly light up Pluto's shadows would require properties far outside the consensus. But here's the twist: dark matter's nature is still unknown. We've never directly detected it, only inferred its presence from the way galaxies spin and light bends. Could there be exotic forms, warm, self-interacting, or even decaying, that behave differently in Pluto's frozen realm? It's a long shot, but science has been surprised before. The real value of this speculation isn't in its plausibility, but in what it reveals about our cosmic blind spots. Dark matter makes up 85% of the universe's mass, yet we know almost nothing about how it operates on small scales. Pluto's pulses, whether tied to dark matter or not, force us to confront how much we still don't understand. Think of it like hearing whispers in a pitch-black room. You might mistake the wind for a voice, but the very act of listening sharpens your senses. For now, the dark matter hypothesis remains on the fringe, overshadowed by more grounded explanations like cryovolcanism or solar wind interactions. But the fact that it's even part of the conversation speaks volumes. Pluto, once dismissed as a static ice ball, keeps defying expectations, daring us to question the boundaries of known physics. Whether dark matter plays a role or not, these pulses remind us that the universe loves a good plot twist, and the next chapter might be stranger than we've dared to imagine. Pluto isn't the only world where darkness hides surprising activity. Its celestial cousins in the outer solar system are just as rebellious. Take Europa, Jupiter's icy moon, where fractures in its frozen shell hint at a subsurface ocean twice the size of Earth. Or Enceladus, Saturn's snow globe moon, spewing geysers of water vapor into space from hidden reservoirs below. These aren't static ice cubes, they're dynamic worlds with internal engines churning beneath their surfaces. And when scientists compare their antics to Pluto's mysterious pulses, patterns begin to emerge. Suddenly, what seemed like an anomaly on Pluto starts looking like part of a much larger cosmic trend. One where frozen worlds defy expectations by staying geologically alive in the cold. Europa offers some of the most striking parallels. Beneath its cracked, icy crust lies a global ocean kept liquid by tidal heating, Jupiter's gravity flexing the moon's core like a stress ball, generating enough warmth to prevent freezing. Sound familiar? It's the same process some researchers suspect might be at work on Pluto, where Charon's gravitational tug could be stirring a hidden sea. Europa's surface also glows faintly in the dark, as charged particles from Jupiter's magnetosphere bombard its ice, creating subtle auroras. While the scale and intensity differ, the underlying physics, external energy triggering light emissions mirrors what might be happening on Pluto's shadowed side. Then there's Enceladus, the overachiever of the Saturn system. Its south pole is a chaos of geysers, erupting water and organic molecules from a subsurface ocean through cracks called tiger stripes. These plumes catch sunlight, creating a shimmering halo around the moon. Now imagine a slower, colder version of this on Pluto. Instead of liquid water, it's nitrogen or methane gas seeping through fissures, ionized by the solar wind or cosmic rays until it flickers with infrared or ultraviolet light. The mechanics aren't identical, but the principal volatile materials escaping from beneath the ice could bridge the gap between these worlds. Even Triton, Neptune's captured moon, joins the conversation. Its surface is littered with cryovolcanos and cantaloupe-like terrain, evidence of past or present geologic activity. Voyager 2 spotted plumes of nitrogen gas rising miles above its surface, backlit by the sun, proof that even at the solar system's edge, ices can erupt dramatically. Triton's thin atmosphere also hosts auroras, sparked by solar wind interactions. If Pluto shares even a fraction of this dynamism, its dark side pulses might be part of a family resemblance among icy, distant worlds. What ties these examples together isn't just similarity, it's diversity. Europa's glow comes from Jupiter's magnetosphere. Enceladus plumes are powered by tidal heating. Triton's eruptions may stem from seasonal sunlight. Pluto's pulses, then, could be a hybrid of these processes: tidal forces, solar wind, and radioluminescence all playing a role. By studying this spectrum of activity, scientists can isolate which variables matter most. Does a world need a subsurface ocean to flicker, or can surface chemistry alone produce the effect? Each comparison sharpens the search for answers. The real revelation here is how wrong we were about the outer solar system. Once dismissed as a freezer full of dead rocks, it's now a gallery of geologically active worlds, each with its own way of staying alive in the cold. Pluto's dark side pulses aren't an outlier. They're a clue in a larger puzzle, one that's rewriting our understanding of where and how celestial bodies can harbor hidden energy. And as missions like Europa Clipper and future probes to the Kuiper belt launch, we're not just exploring individual worlds anymore. We're piecing together a new chapter in planetary science, one where ice, far from being the end of the story, might just be the beginning. Right now, our best window into Pluto's dark side is a narrow one limited to distant telescope observations and data from New Horizons' brief fly by nearly a decade ago. But imagine a spacecraft parked in orbit around Pluto, its instruments trained on that shadowed hemisphere for years, watching as seasons shift and ices crack under the strain of Charon's gravity. Or picture a lander, its sensors pressed against the frozen ground, feeling the vibrations of subsurface oceans and tasting the chemistry of escaping gases. That's the kind of mission it would take to unravel Pluto's pulsating mysteries once and for all. The challenge, distance, and time. Pluto sits so far from Earth that even light takes over 4 hours to make the trip one way. Sending a spacecraft there isn't just a matter of fuel, it's a test of patience. New Horizons, our fastest deep space traveler to date, still needed 9.5 years to reach Pluto after launch. An orbiter would require even more precision, slowing down enough to be captured by Pluto's meager gravity instead of whizzing past. The engineering hurdles are immense but not impossible. Missions like NASA's upcoming Europa Clipper prove we can design spacecraft to study distant, icy worlds in detail. The difference is urgency. Europa has the allure of potential life. Pluto, for now, remains a puzzle without that headline-grabbing hook. Yet the scientific payoff could redefine planetary science. An orbiter equipped with infrared and ultraviolet spectrometers could map Pluto's dark side in high resolution, pinpointing exactly where and when those mysterious pulses occur. A lander, meanwhile, might detect seismic tremors from cryovolcanic activity or sample plumes of gas escaping through surface cracks. Even a simple radio experiment could measure how Pluto's tenuous atmosphere ebbs and flows with the seasons, revealing whether those fluctuations align with the light pulses. Every dataset would be a piece of the puzzle, helping scientists choose between competing theories or forcing them to invent new ones. Until then, researchers rely on clever workarounds. Earth-based telescopes like the James Webb Space Telescope can analyze Pluto's infrared emissions, though their view is blurred by distance. Computer simulations, fed with the sparse data we have, attempt to recreate conditions on Pluto's surface, testing whether tidal heating, solar wind interactions, or radioluminescence could produce the observed signals. It's like trying to reconstruct a symphony from a single note, possible in theory, but fraught with uncertainty. The clock is ticking too. Pluto's atmosphere is collapsing as it moves farther from the Sun in its orbit, freezing back onto the surface. By the 2030-40s, it may be too thin to study meaningfully from Earth. That narrow window makes the case for urgency, not just to solve the dark side riddle, but to witness Pluto's full seasonal drama before the curtain falls for another 2 centuries. What makes this wait so tantalizing is how much we've already learned from limited data. New Horizons' fleeting visit overturned decades of assumptions, revealing canyons, glaciers, and possibly even cryovolcanos. A dedicated mission wouldn't just answer old questions, it would inevitably spawn new ones, pushing our understanding of icy worlds to places we can't yet imagine. Because if there's one lesson Pluto has taught us, it's that the universe saves its most fascinating secrets for those willing to look beyond the light. Pluto's dark side pulses do more than puzzle scientists. They ignite something primal in all of us. There's a reason this tiny world, stripped of its planetary title, still dominates headlines and sparks debates. It's not just about the science, it's about the story. Pluto is the underdog, the cosmic rebel, a frozen understudy suddenly thrust into the spotlight with a performance that defies the script. When New Horizons beamed back those first hazy images in 2015, they didn't just show craters and ice, they revealed a world alive with personality. Mountains as tall as skyscrapers, glaciers of solid nitrogen, and now, a dark side that flickers like a candle in the void. These aren't just data points, they're invitations to wonder. What makes Pluto's mysteries so universally captivating is how they shatter the myth of a static, predictable universe. We're wired to seek patterns, to tidy the cosmos into neat categories. Rocky planets here, gas giants there, icy leftovers relegated to the fringe. But Pluto laughs at those boundaries. Its intermittent light pulses are a cosmic wink, a reminder that the universe thrives on exceptions. For every rule we've etched into textbooks, there's a Pluto waiting to scribble in the margins. And that's exhilarating. It means no matter how much we learn, there will always be surprises lurking in the dark, daring us to look closer. This isn't just academic curiosity, it's a cultural phenomenon. From memes personifying Pluto as a lovable outcast to artists reimagining its landscapes, the dwarf planet has transcended astronomy to become a symbol. It represents resilience, mystery, and the thrill of the unknown. When kids build Pluto dioramas for science fairs or when a new study trends on social media, it's proof that space exploration isn't confined to labs. It's a shared adventure, a collective gasp at the sheer weirdness of the cosmos. The dark side pulses, invisible to our eyes but vivid in our imaginations, are a metaphor for discovery itself. Sometimes the most profound truths reveal themselves only to those who know how to look beyond the visible. But Pluto's greatest gift might be perspective. In a world obsessed with immediacy, this distant, slow-moving world forces us to reckon with deep time. Its 248-year orbit reminds us that some mysteries unfold over centuries, not quarterly earnings reports. The pulses we detect today might be echoes of processes that began before Edison invented the light bulb. There's humility in that. Pluto doesn't care about our deadlines or attention spans. It dances to the rhythm of the universe, and we're just lucky to catch a glimpse. So when we ask why Pluto matters, the answer isn't just in the data. It's in the way this tiny world, against all odds, keeps teaching us to expect the unexpected. Every flicker from its dark side is a whisper. There's more out there, more wonder, more chaos, more questions, and in a universe that often feels vast and indifferent, that's a whisper worth chasing. Pluto's dark side pulses have sparked wild theories from alien megastructures to interdimensional portals, but the truth is far more fascinating than fiction. While it's tempting to let imagination run wild, the real explanations lie in the elegant chaos of chemistry and physics, not little green men. Take the alien beacon myth, for example. Some speculate the rhythmic pulses are intentional signals, but the universe doesn't need extraterrestrial engineers to create patterns. Think of geysers on Earth like Old Faithful, erupting on a rough schedule driven by underground pressure. Pluto's flickers could be just as natural, powered by tidal forces or cosmic rays rather than intelligence. Another popular misconception paints Pluto's dark side as a supernatural void, defying the laws of thermodynamics. But darkness isn't a cosmic anomaly, it's a canvas for hidden processes. Consider how fireflies light up a summer night. Their glow doesn't break the rules of nature, it exploits them. Similarly, Pluto's pulses likely stem from mundane yet extraordinary mechanisms, like solar wind exciting methane molecules or radioactive decay warming subsurface ices. The magic isn't in defying physics, it's in physics working exactly as it should, just in ways we're still decoding. Then there's the myth that Pluto's light phenomena are unique, a cosmic unicorn. In reality, they're part of a broader family of icy world behaviors. Europa's faint auroras and Enceladus geysers show that frozen surfaces can harbor vibrant activity. Even Earth's own polar auroras, sparked by solar particles, prove that light can emerge from darkness without mystical intervention. Pluto's pulses aren't an exception to cosmic rules, they're a reminder of how much we still have to learn about those rules. The most persistent fiction that solving these mysteries would somehow make Pluto less captivating. The opposite is true. Unraveling the science behind the pulses doesn't strip Pluto of wonder, it deepens it. Knowing that tidal heating or radioluminescence might be at work transforms Pluto from a static oddity into a dynamic laboratory, where the universe's most fundamental forces play out in slow motion. The real story isn't about debunking myths, it's about replacing them with something richer, a universe where the ordinary becomes extraordinary when you look closely enough. And that's a truth worth celebrating. Scientists may not have cracked Pluto's code yet, but they've narrowed down the suspects. The leading theories read like a cosmic detective's case file, each clue pointing to a different natural phenomenon, yet none fully explaining the erratic rhythm of those dark side pulses. Surface chemistry tops the list. Picture Pluto's ices not as passive slabs but as reactive canvases, where cosmic rays and solar wind etch invisible signatures. When high-energy particles slam into methane or nitrogen ice, they don't just sit there, they spark chemical chain reactions, releasing energy as faint infrared or ultraviolet light. It's like striking flint in a cave, only the sparks are photons, and the cave is a dwarf planet 4 billion miles away. Then there's the solar wind, that relentless stream of charged particles from the sun. On most worlds, magnetic fields deflect this onslaught, but Pluto lacks that shield. Instead, its wispy atmosphere takes the hit, with solar particles ionizing gases like nitrogen and methane. These excited molecules then shed energy as pulses of light, like embers flaring up in a breeze. The catch: solar wind is constant, but Pluto's flickers aren't. That mismatch hints at another player, perhaps subsurface activity stirring the pot. This is where the plot thickens. Tidal forces from Charon could be flexing Pluto's interior, warming hidden pockets of slushy water or volatile ices. As pressure builds, gases might escape through cracks, bursting into the atmosphere in sporadic geysers. Imagine shaking a soda can, not enough to explode, just enough to let out hissing whispers of gas. Each escape could trigger a pulse, with timing dictated by the slow grind of ice shifting overhead. What's fascinating is how these theories intersect. Solar wind might ignite the pulses, but only when surface chemistry primes the ice, and only if subsurface activity delivers fresh fuel. It's a celestial Rube Goldberg machine, where each step depends on the last. That complexity explains why no single answer satisfies. Pluto's dark side isn't running on one engine but a symphony of them, each instrument playing out of sync. The beauty of this scientific tug-of-war isn't in the certainty but in the collaboration. Researchers studying Pluto's atmosphere team up with chemists modeling exotic ices, while geologists map potential cryovolcanos. Every dataset, from New Horizons flyby to Earth-based telescope observations, is a piece of the puzzle. And as tools improve, like the James Webb Space Telescope peering at Pluto's infrared glow, the picture keeps evolving. For now, the consensus is a humble admission. Pluto's pulses are a masterclass in cosmic subtlety. They remind us that even in the age of high-resolution imaging and supercomputers, some mysteries refuse to be rushed. The dark side's flickers aren't just anomalies. They're an invitation to keep looking, questioning, and marveling at how much we still don't know. And in that uncertainty lies the thrill, because the universe's best secrets are never given up easily. Detecting Pluto's dark side pulses is like trying to photograph a firefly from a moving car at midnight with a camera that wasn't designed for low light. The challenges are staggering, starting with sheer distance. From Earth, Pluto appears as little more than a pixel in even our most powerful telescopes. Its faint whispers of infrared and ultraviolet light drowned out by the cosmic noise of stars, interstellar dust, and our own atmosphere's turbulence. Ground-based observatories like the Keck or the Very Large Telescope can tease out some details, but they're fighting an uphill battle. Atmospheric distortion blurs the signals, and Pluto's 4 billion-mile remove means the light we're straining to see left its surface when smartphones were still a novelty. Enter space telescopes, our eyes above the atmospheric static. The James Webb Space Telescope, with its infrared prowess, is a game-changer theoretically. But even JWST has limits. Pluto's orbit means it's only optimally positioned for observation during brief windows, and the telescope's precious time is split among thousands of competing targets. Capturing those elusive pulses requires not just pointing JWST at Pluto, but staring at it for hours, days, even weeks, hoping to catch a flicker in the dark. It's like waiting for a lightning strike in a thunderstorm that only rolls through once a decade. And even then, the data comes with gaps. Without continuous monitoring, we're left stitching together a stop-motion film of a process that might demand real-time scrutiny. The real hurdle isn't just sensitivity, it's specificity. Pluto's pulses aren't just faint, they're erratic, popping up in unpredictable rhythms that don't neatly align with human schedules or mission timelines. Current instruments are built to study steady phenomena, like the glow of distant galaxies or the heat signatures of exoplanets. Adapting them to catch Pluto's intermittent flickers is like using a net designed for tuna to trawl for bioluminescent plankton. We need detectors with faster reaction times, broader wavelength coverage, and the stamina to watch unblinkingly for years. Then there's the data deluge. Every observation of Pluto's dark side generates terabytes of information, much of it background noise. Isolating the faint signals requires algorithms sharp enough to distinguish between cosmic rays, instrument artifacts, and the genuine article, like picking out a single hushed conversation in a roaring stadium. Machine learning helps, but it's only as good as the training data, and Pluto's quirks keep defying expectations. The stakes are higher than just solving one dwarf planet's riddle. Cracking Pluto's code could pioneer techniques for studying other Kuiper belt objects, or even icy moons around distant stars. Imagine telescopes tuned not just to spot worlds, but to eavesdrop on their hidden activity, surfacing the faint tremors of cryovolcanos on Eris or the nitrogen whispers of Triton's plumes. Every technological leap we make to study Pluto's dark side doesn't just answer old questions. It equips us to ask new ones about the universe's quietest corners. For now, scientists juggle ingenuity and patience, squeezing every photon of insight from the tools at hand. They're racing against time, too. Pluto's atmosphere is collapsing as it retreats from the sun, freezing back onto the surface like a lake locking into winter. Within decades, the very phenomena we're trying to study might vanish until the next cosmic summer. That urgency fuels innovation, pushing engineers to design instruments we've yet to imagine, ones that might one day turn Pluto's dark side into an open book, written in light we're only beginning to see. You don't need a PhD or $1 million telescope to help solve Pluto's dark side mystery. Some of the biggest discoveries in astronomy have started with ordinary people staring at data. Citizen science projects have revolutionized how we explore the cosmos, turning everyday enthusiasts into collaborators on groundbreaking research. Take the Ice Hunters project, where volunteers sifted through telescope images to identify Kuiper belt objects. Some of those discoveries later guided the New Horizons mission itself. Now, Pluto's pulses could be the next frontier for crowd-powered discovery, hiding in terabytes of publicly available data, just waiting for someone to notice a pattern everyone else missed. Platforms like Zooniverse or NAS, a citizen science portal, offer tools to analyze real telescope observations, from spotting surface changes on Pluto to tracking subtle shifts in its infrared emissions. The trick is in the numbers. Professionals can't scrutinize every pixel, but thousands of amateurs working together can cover far more ground. It's like having a global team of cosmic detectives, each bringing fresh eyes to the case. In 2012, a Dutch schoolteacher named Hanny van Arkel discovered a bizarre celestial object now called Hanny's Voorwerp while classifying galaxies online. Could Pluto's next clue come from a curious high school student or a retired engineer poring over data on their laptop? The beauty of this approach is its unpredictability. Algorithms can flag anomalies, but human intuition often connects dots machines overlook. Maybe someone notices that Pluto's pulses sync up with solar wind spikes no one thought to correlate, or spots a faint pattern in the timing that suggests tidal forces at work. Even negative results matter. Ruling out theories is just as vital as confirming them. And with Pluto's data being so sparse, every extra set of eyes increases the odds of a breakthrough. Getting started is easier than you might think. Projects like Backyard Worlds Planet 9 train volunteers to identify moving objects in space images, skills that translate directly to studying Pluto's flickers. Others, like Universe Zoo, focus on classifying light curves, the very data that might reveal Pluto's hidden rhythms. No fancy software is required. Most platforms run in a web browser with tutorials to guide newcomers. The only real requirement is curiosity and patience, because breakthroughs rarely happen overnight. What's at stake isn't just one dwarf planet's secret, it's proof that science isn't an exclusive club. Some of history's most famous astronomers, like William Herschel or Clyde Tombaugh, began as amateurs before their discoveries rewrote textbooks. Today's tools put that same power in your hands, with datasets spanning decades and instruments far sharper than Herschel's handmade telescopes. Pluto's pulses might be the perfect challenge for this era of open science. A mystery just complex enough to stump professionals, but simple enough that a dedicated observer could crack it. So if you've ever stared at the night sky and wondered how you could contribute, this might be your moment. The next clue to Pluto's dark side riddle could be lurking in a spreadsheet or a graph, overlooked until someone like you decides to take a closer look. After all, the universe doesn't care who solves its mysteries, only that someone keeps looking. The question isn't just how we study Pluto, it's whether we should. As our probes and telescopes peel back the layers of this distant world, we're forced to confront a deeper dilemma. Does humanity have the right to disturb a place that's existed untouched for billions of years? It's a debate that splits the scientific community down the middle. On one side, researchers argue that exploration is non-invasive, that our spacecraft are mere observers floating through the void. But others counter that even the act of observation changes what we're trying to study. A lander's heat, a probe's radio signals, or even the faintest contamination from Earth could alter Pluto's pristine environment in ways we can't yet predict. This tension isn't unique to Pluto. It echoes debates from Antarctica's ice shelves to the caves of Mars. How do we balance discovery with preservation? Consider the Mars rovers, meticulously sterilized to avoid contaminating potential ecosystems, or the Lunar Treaty, which designates the Moon as a shared heritage of humankind, free from exploitation. Pluto, though unimaginably distant, deserves the same ethical scrutiny. Its nitrogen glaciers and possible subsurface ocean aren't just scientific curiosities. They're time capsules from the solar system's infancy. Tampering with them risks erasing clues we haven't even learned to read yet. Yet there's another layer to this conversation. If we prioritize preservation over all else, we might miss opportunities to answer existential questions. Pluto's dark side pulses could teach us about the origins of organic molecules or the limits of life in extreme environments. That knowledge might one day save species, or even civilizations, as Earth's climate shifts or asteroids loom. The irony is stark. To protect life at home, we might need to risk disturbing worlds far away. The solution likely lies in nuance. Instead of blanket bans or unchecked exploration, we could adopt guidelines akin to the prime directive from science fiction: minimal interference, maximum reverence. Future missions might use lasers instead of physical probes, or orbiters programmed to decay into harmless trajectories. Scientists are already brainstorming non-invasive instruments like quantum sensors that study Pluto's surface without touching it. These aren't perfect answers, but they're a start. What makes Pluto's case so poignant is its symbolism. It's not just a dwarf planet, it's a mirror. How we treat this distant, frozen world reflects our values as a species. Do we see the cosmos as a resource to exploit, a museum to admire from afar, or something in between? The pulses from Pluto's dark side might be silent, but the questions they raise echo loudly, and how we answer them will shape not just this tiny world's future, but our own. Pluto's whispers from the edge of the solar system do more than tease scientists. They hold up a mirror to humanity's place in the cosmos. Here's a world we once dismissed as a frozen afterthought, now revealing layers of complexity that stump our sharpest mind. Its flickering dark side isn't just a scientific puzzle, it's a cosmic lesson in humility. For all our telescopes, probes, and supercomputers, Pluto reminds us that the universe reserves its most profound secrets for those willing to admit how little they truly understand. Think about it. We've mapped the human genome, split the atom, and touched the moon, yet a dwarf planet 4 billion miles away can still leave us scratching our heads. That's not failure, it's inspiration. This humility isn't about surrender, it's about liberation. Pluto's refusal to fit neatly into our models forces us to confront the limits of human knowledge, and that's a gift. History shows us how often certainty has been the enemy of discovery. When Galileo pointed his telescope at Jupiter, he didn't just find moons, he shattered the illusion that everything revolved around Earth. When Einstein reimagined gravity, he didn't just tweak Newton's math, he revealed a universe far stranger than anyone had dreamed. Pluto's mysteries stand in that same tradition, nudging us to question assumptions we didn't even realize we'd made. Maybe dwarf planet is too small a box. Maybe geologically dead was always a lazy assumption. Every time we hit the edge of our understanding, we're given a choice: cling to old ideas or let the universe teach us something new. There's poetry in Pluto's defiance. While Mars and Venus dominate our fantasies of exploration, this tiny world at the solar system's fringe quietly upstages them with its cryptic light shows and possible underground oceans. It's a reminder that wonder isn't reserved for the obvious places. The universe hides its magic in the corners we overlook, rewarding curiosity over bias. Imagine if we'd stopped probing Pluto after its 2006 planetary reclassification, dismissing it as a frozen relic. We'd have missed the towering ice mountains, the nitrogen glaciers, and now these haunting pulses from the dark. The lesson labels our cages. Reality doesn't care what we call it, only how closely we're willing to look. Pluto's greatest gift might be the way it reframes failure. Every unsolved pulse, every unexplained geological quirk isn't a dead end, it's an invitation. When New Horizons beamed back data that contradicted textbooks, scientists didn't throw up their hands, they leaned in. That's the ethos of exploration at its best, not conquering the unknown, but collaborating with it. The ancient Greeks saw the planets as gods. We've demoted them to rocks and ice. Yet Pluto, with its stubborn mysteries, hints that we might have swung too far in the other direction. Perhaps celestial bodies aren't just objects to catalog, but teachers with rhythms we're still learning to hear. So the next time you feel the weight of the world's unsolved problems, think of Pluto, a speck in the cosmic dark, barely a footnote in most star charts, yet it pulses with questions that redefine possibility. Its flickers aren't just light, they're a beacon, calling us to stay restless, stay humble, and above all, stay curious, because the universe doesn't reveal its secrets to those who think they already have the answers. It whispers them to those who never stop listening. Pluto's journey from astronomy textbook to pop culture icon is as unpredictable as its orbit. Long before New Horizons snapped its first close-up, this tiny world had already carved out an oversized place in our collective imagination. Think of the classic Pluto the pup from Disney, named just months after the dwarf planet's discovery in 1930, forever linking cosmic mystery with childhood whimsy. But that was just the beginning. When scientists stripped Pluto of its planetary status in 2006, the public backlash was fierce. Suddenly, this distant ice ball became a symbol of rebellion, championed by school kids with protest signs and late-night comedians alike. The irony: Pluto's demotion didn't diminish its fame, it supercharged it. Science fiction writers seized on Pluto's mystique, transforming it into everything from a clandestine alien base to the last outpost of a dying human civilization. Arthur C. Clarke's A Meeting with Medusa imagined exotic life forms floating in Pluto's atmosphere, while Kim Stanley Robinson's 2312 painted it as a hub for quantum experiments. These stories thrive on Pluto's real-world contradictions, a world too small to be a planet, yet too complex to ignore. Now, with the discovery of those eerie dark-side pulses, creators have fresh fodder. Recent novels like The Pulse of Pluto weave conspiracy theories around the flickers, suggesting everything from ancient alien beacons to interdimensional rifts. Even music and art can't resist Pluto's gravitational pull. Indie bands pen lyrics about its icy loneliness, while digital artists reimagine its surface as glowing with bioluminescent frost. The dwarf planet's reclassification birthed an entire genre of Pluto protest songs, blending scientific literacy with punk rock defiance. And let's not forget memes' endless variations of Pluto as the solar system's disgruntled underdog, glaring at Neptune from the cosmic kiddie table. What makes Pluto's cultural footprint so enduring isn't just its astronomical quirks, it's the humanity we project onto it. We see ourselves in its struggles, too small to compete with giants, yet too unique to be forgotten. The dark side pulses add a new chapter to this mythos, casting Pluto not just as an underdog, but as an oracle. Every flicker feels like a coded message, inviting us to project our wildest theories onto the cosmic void. Whether it's sci-fi authors or TikTok creators, we're all united by the same impulse: to look at Pluto's shadows and see stories waiting to be told. The beauty of this cultural dance lies in its two-way street. Just as Pluto inspires artists, those creations loop back to shape real science. Public passion for Pluto helped secure funding for New Horizons, proving that what captures our imagination can also drive discovery. Now, with each new theory about those dark side pulses, from cryovolcanos to cosmic rays, we're not just solving equations, we're continuing a conversation that began decades ago, when a cartoon dog and a lonely ice ball first collided in the public consciousness. Pluto may orbit in silence, but here on Earth, its legend echoes louder than ever. Pluto isn't just a distant world, it's a classroom without walls, where every unsolved mystery becomes a lesson in how science really works. Imagine a high school student staring at data from New Horizons, tracing those erratic pulses of infrared light and wondering, what could possibly cause this? There are no tidy answers in the back of the textbook here. Instead, they're handed the same raw puzzle that has professional astronomers scratching their heads, learning firsthand that science isn't about memorizing facts, it's about wrestling with the unknown. This is where Pluto shines as a teaching tool. Unlike polished theories about planetary formation or gravity, its dark side pulses are a live demonstration of the scientific method in action. Students can watch as researchers propose, test, and discard explanations from tidal heating to cosmic rays, seeing up close how evidence shapes understanding. It's messy, thrilling, and deeply human. One day, the leading theory might be cryovolcanos, the next, a peer-reviewed paper COULD Chinese letter it with a new simulation. That uncertainty isn't a weakness, it's the essence of discovery. For a kid raised on flashcards and multiple choice tests, realizing that even NASA doesn't have all the answers can be revolutionary. Hands-on projects bring Pluto's mysteries down to Earth. Picture a science fair where teams build models of Pluto's subsurface ocean, testing how different ice thicknesses affect hypothetical geyser eruptions. Or a coding club analyzing real telescope data, hunting for patterns in the pulse timing that automated algorithms might have missed. These aren't hypotheticals. Programs like NASA, a solar system ambassadors already partner with schools to turn raw mission data into student projects. When kids engage with authentic, unsolved problems, they're not just learning science, they're living it. The ripple effects go beyond STEM skills. Pluto's story teaches resilience. When the International Astronomical Union reclassified it as a dwarf planet in 2006, the backlash wasn't just from astronomers. Kids wrote impassioned letters defending Pluto's planetary status. That emotional connection is priceless. It shows them science isn't static. Definitions evolve as our knowledge grows. Today's students might be the ones to redefine what planet means, or to prove Pluto's dark side pulses are evidence of something no one's even considered yet. Universities are taking note. At labs like MIT's Planetary Science Group, undergraduates contribute to published research on Kuiper belt objects, proving you don't need a doctorate to advance the field. Online platforms like Zooniverse let anyone classify Pluto's surface features from their phone, turning passive observers into active participants. This democratization of discovery sends a powerful message. The next breakthrough could come from anywhere. Maybe it's a rural student with a homemade radio telescope, or a teenager spotting an anomaly in publicly available data. Pluto doesn't care about credentials, it rewards curiosity. What makes this more than just academic is the bigger picture. Solving Pluto's riddles could unlock secrets about other icy worlds, from Europa's hidden ocean to the nitrogen geysers of Triton. The same tools students master today, spectral analysis, orbital mechanics, even machine learning, might one day decode signals from exoplanets light years away. By starting with Pluto, they're not just learning science, they're rehearsing for humanity's next great explorations. So while researchers debate theories, classrooms are quietly nurturing the minds who'll settle those debates. Somewhere right now, a future planetary scientist is sketching Pluto's terrain. A budding engineer is prototyping a low-temperature spectrometer, or a young coder is training an AI to predict pulse patterns. They're proof that Pluto's greatest legacy isn't just what it teaches us about the solar system, but who it inspires to keep asking questions, and in the end, that might be the most important light it shines. To understand Pluto's cryptic light pulses, scientists don't just stare at telescope data, they build entire digital replicas of the dwarf planet, tweaking variables like cosmic chefs perfecting a recipe. These aren't simple animations, they're hyper-detailed simulations running on supercomputers, where every pixel of Pluto's surface is coded with real-world physics. Imagine a virtual laboratory where researchers can crank up the solar wind, freeze the atmosphere solid, or tilt Charon's gravitational pull, all to see which combination makes the dark side flicker like the real thing. It's cosmic detective work, but instead of fingerprints, they're tracking the faintest echoes of infrared and ultraviolet light. Take the subsurface ocean hypothesis. Plugging tidal forces from Charon into these models reveals how heat might ripple through Pluto's interior, cracking the icy shell above. The simulations show stress points where geysers could erupt, their timing syncing or clashing with the observed pulses. But here's where it gets clever. When scientists tweak the ocean's salinity or depth, the results shift. A saltier ocean stays liquid at lower temperatures, potentially prolonging geological activity. Too shallow, though, and the fractures don't reach the surface. It's like tuning a radio, searching for the frequency where theory matches reality. Then there's the chemistry of Pluto's ices. Methane and nitrogen aren't just passive frost, they're dynamic substances that behave unpredictably under extreme cold and radiation. Simulations let researchers bombard virtual ice sheets with cosmic rays, watching as bonds break and reform, releasing bursts of energy. Some models suggest pockets of pure nitrogen ice could act like lenses, focusing solar wind particles into hotspots that glow under the right conditions. Others explore how methane clathrates those cage-like structures trapping gases, might shatter under pressure, creating delayed light emissions. Each simulation is a digital petri dish, culturing answers from the void. The real power of these models lies in their ability to fail. When a simulation's pulses don't match New Horizons data, it's not a dead end, it's a clue. Maybe the solar wind's intensity was underestimated, or Pluto's crust is thicker in certain regions. These discrepancies force scientists to revisit assumptions, refining their digital Pluto until it hums in harmony with the real one. It's a process akin to sculpting, chipping away at the marble of uncertainty until the shape of truth emerges. What's astonishing is how these virtual experiments bridge gaps in our physical reach. With no orbiter currently watching Pluto, simulations become our time machine, replaying centuries of seasonal changes in hours. They reveal how pulses might crescendo as Pluto nears the Sun, then fade into silence during its long retreat. Or how cosmic rays, though random, could create pseudo-patterns when averaged over decades. Every pixel in these models is a question. What if, and with each iteration, Pluto's dark side feels less like a mystery and more like a story we're learning to read one line of code at a time. Pluto's dark side pulses aren't just a scientific challenge, they're a diplomatic handshake. Solving this cosmic riddle demands more than one nation's brainpower. It requires a symphony of global expertise, where researchers from NASA, the European Space Agency, Japan's JAXA, and beyond trade data like puzzle pieces. Picture the control room during New Horizons flyby. Engineers in Maryland monitored propulsion while astronomers in Germany calibrated spectrometers, and Chilean telescopes tracked the spacecraft's trajectory. This wasn't just teamwork, it was a real-time experiment in how science transcends borders. The beauty of this collaboration lies in its diversity of perspectives. At MIT, planetary scientists model Pluto's subsurface ocean using fluid dynamics, while in Paris, chemists simulate how cosmic rays fracture methane ice. Russian astrophysicists contribute insights on solar wind interactions, honed from decades studying Earth's magnetosphere. Each approach is a lens, none complete alone, but together they sharpen the image. When Japan's Subaru telescope detected an unexpected infrared spike from Pluto's shadowed regions, that data didn't stay in Tokyo. It pinged across servers to Arizona, where researchers cross-referenced it with decades of NASA Hubble archives. The result, a eureka, a moment no single team could have achieved. This spirit of shared curiosity even overrides earthly tensions. During political standoffs between their governments, American and Russian scientists kept collaborating on Pluto's atmospheric models, united by questions bigger than geopolitics. The International Astronomical Union's working groups, where researchers from India, Brazil, and South Africa debate definitions of dwarf planets, prove that scientific progress thrives when borders blur. It's not just about pooling resources, it's about multiplying creativity. A theory dismissed in one lab might spark a breakthrough in another, like ESA's discovery that Pluto's nitrogen glaciers flow differently than Earth's, a finding that reshaped how NASA interprets those dark side pulses. The technology enabling this cooperation is as groundbreaking as the science. Cloud-based platforms let teams analyze the same dataset simultaneously from different continents, annotating findings in virtual war rooms. Machine learning algorithms trained on contributions from dozens of institutions now flag anomalies in Pluto's light patterns that human eyes might miss. Even language barriers crumble with AI-powered translation tools, letting a young researcher in Beijing seamlessly discuss cryovolcanism with a veteran professor in Lisbon. What's at stake goes beyond Pluto. These collaborative frameworks are blueprints for future exploration of Europa's ocean, Titan's methane lakes, or exoplanets light years away. Every protocol refined, every data-sharing agreement signed to study Pluto's pulses makes humanity better prepared for the next great cosmic mystery. Because if a tiny world at the solar system's edge can bring nations together in wonder, imagine what else awaits in the dark. For all the theories and simulations, Pluto's dark side pulses still guard their deepest secrets. One of the biggest unknowns, whether these flickers light up the entire shadowed hemisphere or cluster in specific hotspots. New Horizons' fleeting glimpse suggested irregularities, brighter patches near mountain ranges or crater edges. But without sustained observation, we can't tell if those were fleeting anomalies or permanent stages for these cosmic light shows. If the pulses are localized, it could point to geological activity beneath the ice, like cryovolcanos or gas vents. But if they're uniform, that might hint at atmospheric phenomena, like solar wind interactions blanketing the entire dark side. The difference isn't just academic, it's a roadmap for future missions telling engineers where to aim their instruments. Then there's the mystery of timing. Some pulses seem to arrive in clusters like Morse code with a stutter, while others flicker solo. Do these rhythms sync with Pluto's elliptical orbit, suggesting solar influence? Or do they match Charon's gravitational tugs, implying tidal forces at work? The data we have is too sparse to say, like trying to predict a thunderstorm from a single raindrop. Even more puzzling, a few pulses appear to coincide with bursts of cosmic rays detected by Earth-based observatories. Is that coincidence, or could interstellar particles be triggering these flashes? Without long-term monitoring, the patterns remain just out of reach, taunting researchers with fragments of a cipher they can't yet crack, the wild card. Whether these pulses are solo acts or part of a larger cosmic ensemble, on Earth, auroras often dance alongside magnetic storms and solar flares. On Pluto, do the dark side flickers correlate with changes in its wispy atmosphere or tremors in its icy crust? Imagine discovering that every pulse is preceded by a subsurface quake, evidence of a hidden ocean sloshing beneath the ice. Or perhaps they're tied to seasonal shifts, with pulses intensifying as Pluto's nitrogen snows vaporize under the weak summer sun. Right now, these connections are threads dangling in the dark, waiting for someone to weave them into a tapestry. What makes these unanswered questions so thrilling is how they reframe Pluto from a static world to a dynamic puzzle. Every unsolved riddle is an invitation, not just for scientists, but for anyone staring at the night sky and wondering what's out there. The pulses could be whispers from Pluto's interior, clues about the Kuiper belt's history, or even a window into how icy worlds across the galaxy behave. Until we send another mission or train sharper telescopes on its shadowed side, those whispers will stay just loud enough to keep us leaning in, listening closer, and daring to imagine what else might be hiding in the dark. Pluto's dark side pulses aren't just scientific anomalies, they're cosmic breadcrumbs, leading us deeper into the universe's grand puzzle. Every flicker of infrared or ultraviolet light is a question mark written in wavelengths we're still learning to read, a reminder that even in the age of high-resolution telescopes and interplanetary probes, the universe holds cards close to its chest. Think about the sheer improbability of it all. A world smaller than Earth's moon, spinning in the frigid outskirts of our solar system, somehow defying expectations by pulsing with energy where none should exist. It's as if the cosmos is whispering, "You think you've got me figured out? Think again." The theories we've spun to explain these pulses, subsurface oceans churning under ice, solar wind sparking chemical reactions, even the wild card of dark matter interactions, aren't just competing ideas. They're a celebration of human ingenuity, a testament to how far we've come since Galileo first pointed his telescope at Jupiter. Centuries ago, planets were mere wanderers against the stars. Now, we're debating the geothermal activity of a dwarf planet 4 billion miles away. Yet for all our progress, Pluto's stubborn refusal to fit neatly into our models is a humbling counterbalance. The more data we collect, the clearer it becomes. This tiny world operates on a logic we've yet to fully grasp. What makes this mystery so exhilarating isn't just the destination, it's the chase. Science thrives on the unresolved, the anomalies that keep us up at night. Consider how Pluto's reclassification in 2006 ignited public passion, proving that celestial underdogs can capture hearts as fiercely as gas giants. Or how New Horizons, a mission decades in the making, rewrote textbooks in a single flyby. Those grainy images of towering ice mountains and nitrogen glaciers didn't just fill gaps in our knowledge, they tore open new ones. And now, these enigmatic pulses add another layer, proving that Pluto's greatest gift might be its ability to keep us curious. The road ahead is as uncertain as it is exciting. Future missions like NASA's proposed Persephone orbiter or private ventures aiming for the Kuiper belt could one day park a spacecraft above Pluto's dark side, watching those pulses in real time. Telescopes like the upcoming 30-meter telescope might dissect their spectra with unprecedented precision. But here's the beautiful paradox. Even as we inch closer to answers, Pluto will always find ways to surprise us. Maybe the pulses are caused by something no one's even hypothesized, yet a phenomenon so alien it reshapes our understanding of icy worlds altogether. So while we wait for the next breakthrough, let's savor the mystery. Pluto's intermittent light isn't just a scientific riddle. It's a beacon calling us to stay restless, to keep probing the shadows for clues. In a universe that often feels vast and indifferent, these flickers are a reminder that wonder isn't reserved for the obvious or the grandiose. Sometimes it's hiding in the quietest corners, waiting for someone to look closely enough to see. And that's the real lesson here. The cosmos never runs out of secrets. It just asks us to keep listening. So what's your take on Pluto's cryptic light show? Do you think tidal forces from Charon are flexing its icy shell? Or could those pulses be cosmic rays igniting chemical reactions in the frost? Maybe you've got a wild card theory like dark matter interactions or radioactive decay in Pluto's core. Drop your thoughts in the comments below. Some of history's biggest discoveries started as bold guesses, and yours might spark the next aha moment. While you're there, hit that like button if you enjoyed unraveling this cosmic whodunit, and subscribe to join our crew of space detectives, because here's the thing, Pluto's just the beginning. The Kuiper belt's packed with icy oddballs whispering their own riddles, and with your curiosity fueling the journey, who knows what mysteries we'll decode next. Until then, keep looking up and remember, even in the darkest corners of space, there's always a flicker waiting to